Aqueous solutions and solubility, compounds dissolved in water. Well, we mentioned aqueous solution when we talked about those state symbols, the indication in a chemical reaction that a substance is dissolved in water. We're going to talk a little more about what does that mean. An aqueous solution is a homogeneous mixture of a substance with water. So homogeneous means the same throughout, it's uniform. There's no chunks or lumps or layers or anything. What happens when ionic compounds dissolve in water is they usually dissociate or come apart into their individual ions. So sodium chloride has sodium ions and chloride ions. You can try this at home. Take a glass of water and a teaspoon of table salt, put it in the water, and stir. It seems like the salt is disappearing. You can't see it anymore. But it's still there. And if you don't believe it's still there, taste the water. Be ready to spit it out. It's not going to taste very good. But you can taste it. It's salty, so it's still there. But the sodium ions and the chloride ions have separated from each other and mixed thoroughly with the water. They formed an aqueous solution. So here's a picture. When we make an aqueous solution of sodium chloride, this is what we have. We have sodium ions and we have chloride ions, and they're uniformly distributed throughout the water. There are no sodium chloride units. They all separate. And we have a special word for substances like that. Substances that completely dissociate into ions are called strong electrolytes. There are strong ones and there are weak ones. These are strong electrolytes. And you maybe have heard the word electrolyte in conjunction with exercising and being dehydrated and Gatorade and other sports drinks, right? Oh, you need to drink Gatorade to replenish your electrolytes. Yeah, your body needs soluble ionic compounds to function. And when you sweat excessively, there is salt of more than one kind that comes out in your sweat. I know my husband's gone and played golf in the middle of August in 106. And, you know, his shirt is like wet. And by the time he comes home, it's dried off again, but there's all this white residue on the shirt. That's the salt that was in his sweat. That's what you need to replenish when you're exercising and sweating profusely. Now, if you're just working up a little glisten, water's going to do you just fine. But these are strong electrolytes. The term electrolyte comes from electrical conductivity. Here's a little apparatus where we have a battery and a light bulb. And instead of these two wires being connected to each other, we stick them into a glass of water. If you have pure water, it doesn't matter how big the battery is. Well, I take that back. The light bulb's not going to light up. You're not going to get electric current flowing through this to light up the light bulb. Throw a little bit of table salt in there, and the light bulb lights up. What's going on? Well, electrical current is the flow of electrons. And in order for the light bulb to light up, the electrons have to be able to flow. They need a closed circuit to flow through the light bulb. When we have ions in the solution, the ions can carry the electrical charge. No ions, no conductivity. So, strong electrolytes conduct electricity strongly. Now, why have you been always warned all your life to be very careful around electricity and water? So, you could get electrocuted, right? But you just said pure water doesn't conduct electricity. Yeah, but if you're standing on your flooded patio messing around with extension cords, is that pure water you're standing in? No. It's going to have dirt and dissolved ions and stuff. And even tap water has enough ions in it to conduct some electricity. So you still need to be careful around electricity and water. Silver nitrate also dissolves in water. Here we have the silver ions and the nitrate ions. This is also a strong electrolyte solution because it completely comes apart into its individual ions. What's important to notice is that this polyatomic ion, nitrate, does not come apart. The oxygen atoms and the nitrogen atom are covalently bonded to each other. Think superglue. So this ionic bond is like a magnet, and this covalent bond is more like superglue. It does not come apart, but the sodium, there's no sodium. The nitrate, that's what that is. The nitrate ion can come away from the sodium atom. The nitrate ion itself is going to stick together. So polyatomic ions do not come apart when you dissolve the solution. Dissolve the compound. It's only 1:25. It's not time for bed yet, is it? What about silver chloride? Put silver chloride in water, and it sits there like a lump in the bottom of the beaker. It does not come apart. What's up with that? It's an ionic compound. Why doesn't it dissociate into its ions? Because not all ionic compounds are soluble in water. The reason for that is complicated and beyond the scope of this class. We do understand, but it's not a simple matter to explain, so we're not going to try. So some compounds don't dissolve. Silver chloride is one of them. It's just going to sit there. It doesn't separate into ions. Is it a strong electrolyte? No. In fact, it's called a non-electrolyte because it really just doesn't dissolve at all. So solubility. We say a compound is soluble in a particular liquid if it dissolves. If you put it in, you stir it up, and it dissolves and mixes, then it's soluble. It doesn't have to be water. There are other liquids that you can dissolve things in. Just mostly water is what we talk about. We say a compound is insoluble, not soluble, if it doesn't dissolve in that liquid. So we have some empirical rules of solubility. Empirical, derived from experiment. These are observations. They're useful, but there are exceptions, and the solubility rules are in table 7.2. There are many exceptions to these. So here's the table. Your book also gives a flowchart version. I find that the table version works for more people, and so I'm going to ignore the flowchart one. But I will give you this table on an exam. I make the 1A students memorize this, but the 3A students, I just want you to learn how to use this table. So in the top part of the table, these are compounds that are mostly soluble. Compounds containing these ions, lithium, sodium, potassium, those are alkali metals, and ammonium. And then there's a listing of exceptions. There's no exceptions to those. What that means is if you have any ionic compound that's got lithium in it, it's going to be soluble. And then here are a couple of anions, nitrate and acetate. These guys are soluble, no exceptions. Chloride, bromide, and iodide, the halide ions. These are mostly soluble except when they're with silver, mercury 1, and lead 2. Then they're not soluble. So silver chloride, we just looked at that, not soluble. Potassium chloride, that one's soluble. And then sulfate. Sulfate is soluble except with strontium, barium, lead, or calcium. So calcium sulfate, not soluble. So that's the mostly soluble. And then on the bottom are things that are listed as mostly insoluble. So hydroxides are insoluble except with those guys, because these guys at the top had no exceptions. Lithium, sodium, potassium, ammonium, those are always soluble. Sulfide ion, again, with one of those four, it's soluble. If sulfide pairs with calcium, strontium, or barium, it's also soluble. And hydroxide with one of these is slightly soluble. Okay, so slightly soluble, asterisk, for many purposes these can be considered insoluble. So we're going to go with that. If it's slightly soluble, we're going to say, well, it just dissolves a little bit, but generally it's insoluble. And then carbonate and phosphate ions. Anything containing carbonate and phosphate is probably going to be insoluble, except with those guys. So that's the table. Aren't you glad you don't have to memorize that? We just need to learn how to use it. So let's practice. Is each compound soluble or insoluble? So CuS. So what we need to do is we need to look for those two ions in this table. So we start at the top and we go down CuS, CuS. Oh, here's S. S compounds, sulfides, are mostly insoluble except with those or with these guys. Is copper one of those exceptions? No. So that tells us that copper sulfide is insoluble. Insoluble. How about iron 2 sulfate? Well, again, start at the top. We're looking for iron or sulfate. Oh, there's sulfate. Over here are the exceptions. Is iron one of the exceptions? No. Not an exception, so this sulfate compound is soluble. Lead carbonate. Well, start at the top, looking for lead or carbonate. No. Oh, there's carbonate. So lead carbonate compounds are mostly insoluble except with these guys. It doesn't mention lead. So it's insoluble. How about ammonium chloride? So here's NH4, that's the ammonium. These are mostly soluble, no exceptions. We don't even have to look at the other ion. If we did look at the other ion, we'd see here's chloride, and those are the exceptions, but ammonium isn't one of them. So this one's soluble. Any questions? I'll give you that exact table on the exam. It's in your book, so practice using it.